Cloud. Okay, wonderful. Hello,
All
everyone.
right.
Welcome to another episode of the GPU Mode. Today, I'm really thrilled to invite Arun Demeure. So a lot of y'all might recognize Arun as one of the core developers behind LMC. He's been someone who I see like regularly helping out people like in various channels, and someone's like knows like a lot about GPUs. I think this is our lowest level talk yet. Like basically, Arun's going to be talking about SASS and GPU microarchitecture. So Arun, without further ado, please take it from here.
Thank you. Yeah, I guess in terms of background as well, before I worked at M.C and other open source projects, I was a GPU architect at Imagination and shortly for about 2 years at Apple. So I worked on sort of processors from both the software and hardware side. And my background kind of therefore makes me very curious to go as deep as I possibly can and try to actually figure out how it works. And hopefully this will help some people to do better optimizations as well. I think the first kind of thing I need to clear out is people think about SAS and GPU assembly, you might assume you're going to run to write GPU assembly directly. But actually, it turns out that so it, and ironically, H100 is one of the only NVIDIA GPUs without a fully working open source assembler. Like you can use QAssembler, it kind of works, but it doesn't actually support everything, and no one's ever forked it to fix all the issues. So actually, you cannot write fully custom SAS out of the box with only open source programs. So what's the point of studying it if you cannot actually change it? What's the point of actually knowing how it works if you have no actual direct control of it? And I kind of look at it as the same way as why would you want to know your own DNA and like, oh, it helps you diagnose disease and then hopefully get better treatment. So I really like this chart from Philip Tillet's presentation. He's the creator of Triton, about how effectively, until you put in a large amount of time, which is both time in terms of training yourself and in terms of optimizing the kernels, uh, actually an high-level language like Triton will be higher performance. And then at some point, once you've put in enough effort, again, all depending on the complexity of the kernel, you'll end up beating Triton. And if you do SAS, you could theoretically do even better, but at a much, much higher cost to get there. I think like the exact shape of the graph isn't the way I would think about it, especially because the bigger problem is you kind of have the bars there at the very bottom for longer because it takes longer to get anything at any level of performance working. You have to be functionally correct. But I think that's kind of the wrong way to think about it. Actually, what you want to do is you want to understand the hardware and understand the assembly so that you can optimize what you've got in high-level frameworks like Triton and CUDA, so that you can then write better CUDA or better Triton. And if you look at only what's in the PMPP, Programming Massively Parallel Processors book, it's actually not really enough to beat Triton in some cases. Like, for example, it doesn't even really talk about vector loads and lots of hardware details that NVIDIA does talk about in GTC presentations. So if you're only using what's in the PMPP, given the fact that Triton does a bunch of optimizations automatically, you will probably fail at even achieving as high performance as those high-level kernels, which is partly why I think like Onslaught, Liga, and loads of other things have done a really amazing job in terms of improving GPU performance are all based on Triton. But there's still an opportunity to do even better, both with custom kernels and, well, also compiler engineers improving all of this. And so you just need to effectively change the right way you write CUDA and change the way you profile to then improve performance. So this is kind of an aside, but I think it's really important. The way I think about performance is what you actually care about is iteration time. And as part of that, if you do a very long training run that takes 2 months, that is part of your iteration time. And something that's happened recently that's really interesting is modern general GPT, and that they've managed to speed run effectively training Nano GPT to a certain level of quality in only 5 minutes. Um, I feel like that's a good example of iterating at eye level with PyTorch being much more efficient than using CUDA. If we had to write all of those kernels and all the experiments they did in CUDA, it would have taken forever. On the other hand, once you do a longer training run, potentially that changes. And ironically, right now, from the data I've seen, Torch compile takes longer than the speedrun itself. Like from scratch, I think they said it's 10 minutes, and with cache, it's like 5 minutes. So it's about the same time as the speedrun itself. Um, I kind of just want to highlight that you have to be very careful not to do low-level optimization before you've done other ones. Um, on the other hand, like if it does at a certain scale, you will actually get a significant benefit. Um, and hopefully, lots of optimizations are not that hard. You just need to know they're possible. Flash attention is a good example of like optimizing algorithm big O complexity before you do low-level optimization, and then you do things like flash attention tree to kind of get the absolute maximum of that better algorithm. So I feel like at the point where you're doing like absolutely gigantic clusters, like thinking about ON is kind of wrong metric because effectively everyone has already optimized that and everyone is using the best algorithms that we know of. And it's kind of about potentially squeezing that last 1, 10, maybe 20%, probably more like 1% in many cases, but even that can be worthwhile. And so I kind of want to introduce another metric rather than ON, which I call ONR, optimization per nuclear reactor. And if you look at the scale of these clusters and the size of SMR, which is about 50 megawatts, um, you do end up with a reasonable percentage of the cost of a nuclear reactor in terms of power efficiency by just optimizing by 1%. Actually, though, it's much, much more than that. So NVIDIA is not just selling GPUs for one cluster, they're selling GPUs for, well, many, many, many large clusters. And if you do some Jensen-style CEO math, you end up with about 5 million GB200 equivalent over its lifetime at a kind of very conservative minimum, assuming they meet their forecast, and you end up with 10 gigabytes of power. That means that 1% of performance per watt, where you actually reduce the power and increase the performance so that you have 1% higher performance at the same power as before, or same performance, 1% power less, is equivalent to 2 small nuclear reactors. Now, in the end, I personally don't care as much about that, about just the fact that it's fun. And I feel like it's obviously worth knowing just because if you're going to work on this kind of thing, you will feel much more satisfaction when you actually understand the details. On the other hand, sometimes it is very frustrating and it's very easy to underestimate how complicated an optimization is and how hard it is to get to the speed of light. So this presentation isn't going to focus on tensor cores. It's not going to focus on Mode 800 specific things. I will have a bunch of live demos, some of which are well prepared, some of which are not. We'll kind of see how we do on time for lots of these things. So this slide I put in the Triton channel earlier to sanity check if it's correct. I don't think anyone replied, so I'm going to naively assume that it is correct for the Triton, PyTorch, and MLR sites. So what I'm trying to show here is that there's lots of different ways that PTX gets generated as part of machine learning frameworks. And NVCC being the main one for CUDA, but NVCC isn't actually used for Triton. And potentially for cuBLAS, it's custom PTX in certain cases and so on. However, it all passes through PTX-AS, which is the optimizing backend compiler. And it does a lot of optimizations, actually. So you cannot just look at PTX and assume that it's really relevant for performance. It's an important thing you need to look at, but personally, I typically look at PTX after SASS, like in order to understand why the SASS is a certain way if it's not obvious to me from the CUDA. Might be different for Triton, but the other thing I wanted to highlight is there are actually other ways to generate SASS. There are loads of open source assemblers, and I'll put that in the next slide. And there's NVK, which is quite interesting because in the past, open source NVIDIA drivers were, well, to put it mildly, kind of terrible. NVK is actually really good. And they've managed to make their own fully custom a Vulkan compliant backend compiler that generates SASS completely from scratch with no code from NVIDIA. And this is kind of an interesting reference for some of the like lower level details. You can look to the chat logs of their RC channels and just like the code and so on in order to understand some of the very final details if you really want. Obviously, that doesn't tell you everything because the driver sometimes doesn't even need to know about the way the hardware works, but it's an interesting other source of information. So this is just a list of the different assemblers. QAssembler is kind of the most modern recent one, but unfortunately it's not been maintained either. MaxSASS by Scott Gray is the most well-known one. Um, I think people do tend to overestimate or correct it still is. So for example, so one thing I'm not going to touch in this presentation is the reuse register flags in the SASS because of I've got patents in that topic and other things. So I really shouldn't talk about it. But I know, as a matter of fact, that everything in Maxwell has changed quite a bit in Volta. And similarly, because no one's done that level of analysis since then, I have noticed some things which are just kind of subtly wrong. Uh, a few other interesting projects is NV Solver, which I'll go to afterwards again, Document SASS, and NVBit. I think except for NV Solver, I won't really have the time to go into those today. So this slide is kind of a very high-level view of all the different NVIDIA GPU generations. And it's a lot. And as the next slide shows, actually, you probably only have to care about upper and Ada, which is one kind of family. And the instruction set has remained quite constant since Volta. Like, well, there's been loads of change, loads of improvement, but at eye level, it's still quite similar. So I think the amount of diversity and complexity in GPU instruction set is really interesting. And for example, I don't know many people realize that the original G80 in 2006 was kind of the very first CUDA GPU. In some ways, was really quite a KISC instruction set, like complex instruction word like x86. It didn't, not in all ways, but for example, shared memory loads and stores were part of the instruction. And these things kind of evolve over time. And the reason I mentioned that is the interesting change in Opera that it finally got rid of constant memory. As far as I can tell, at least as far as the compiler uses, it finally got rid of constant memory accesses as part of the instruction, which I'll touch on later. And that kind of makes it more risk. But again, compared to everything else that goes on in these instruction sets, like risk versus KISC is like kind of irrelevant. What actually matters is everything else and the way instructions get executed on the hardware. So let's see how this goes in terms of just showing actual PTX and SASS. Let me actually take Godbolt. It's kind of a nice first thing. Let's see. So for those who are not familiar with Godbolt Compiler Explorer, it's amazing. It's an online thing. You can also run it locally with your own compiler if you want to, but I typically don't tend to bother doing that. It updates instantly, so you can just kind of do this, and it will then update here in a second. So this is a very simple program. The PTX looks like this. The SASS looks like this. Something else to point out. Okay, not sure that matters in Godbolt. So no, it doesn't. That's for the CPU side. So this tells you you're compiling for upper specifically. I think something that's really important to realize is that PTX is forward compatible. So for nearly without exception, as far as I can know, you could run even like G80 PTX on upper. However, there's new PTX instructions that get added over time. And those PTX instructions may allow the compiler to use some hardware instructions that otherwise would effectively be emulated. So it's really important that you compile for the latest PTX, which is not the default when you make a create a program from scratch. because while it will run, because effectively the PTX is embedded in the application, it compiles to the actual SAS assembly afterwards when you run the binary, but it doesn't have access to the PTX that's been optimized for that specific architecture. So it's both the PTX and SAS that need to be for that architecture for maximum performance. By the way, everyone is very welcome to interrupt me for questions, especially during the live demo parts, because otherwise it might get boring as I kind of fix things and show things. This is kind of something else I wanted to highlight, and I think I can probably highlight it best with, no, it's going to be too complicated to get working potentially. I had like the div view in there, but I lost it. So instead, let me just highlight it by changing to Volta, which is SM70, and point out that it's both very similar and very different. So previously, so the kernel arguments and constant values and a bunch of other things get passed to constant memory. On Volta, you will see things like C and a specific address, even part of arithmetic instructions. So this is an integer multiply at. The constant memory fetch is part of the instruction. It's a location in DRAM. No, it's got a maximum size like 64 kilobytes and things like that. But it is in DRAM. It could miss all the way to even like potentially system memory. Actually, no. I think it could miss to the it could miss in the memory units and kind of end up taking more memory management units and take more than 1,000 cycles. So you've got a random thing and a random instruction storing everything for 1,000 cycles, which is extremely rare in practice, but it kind of highlights the complexity of the architecture that something like that is even possible. When we move to Hopper, all of that is gone, and starting in Turing, which I'll go to afterwards, they've introduced uniform registers, which are per warp or yes, per warp, as opposed to being per thread. Typically, the compiler will end up realizing it can use it based on the fact that it's constantly the entire thread group. It's kind of tricky for the compiler to figure out in some cases where it can use uniform registers. And you don't have any access to that, not just in CUDA, but in PTX. So it's a good example of something where you want to write your code in such a way that the compiler is able to use them. And it may not always be obvious what the right code for that is. So I want to very quickly go through the different instructions here. This is, right, actually, something else to highlight. So there is no proper documentation of the details of each instruction. If you go in Godball, go for view assembly, you've got this page. And in this NVIDIA documentation, you've got a list of all the instructions and literally like just the name of it, which tells you what the acronym stands for. But there's no documentation officially from NVIDIA besides that of any kind. There is, actually, maybe it's worth pointing this now rather than if I go NVIDIA as a sort of finding the link. So this is a really cool project that I think was done this summer of someone reusing the parser from QAssembler and adding a really clever way to kind of brute force all the possible encodings and get the assembly and then visualizing this. So you then represent the actual instructions this way, and you can kind of see both the encoding and what the different options are. However, that doesn't really tell you like how things work. Like here's a branch instruction, here's a bunch of modifiers without documentation, what operand types are supported in some cases, like what are barrier registers, none of that is documented. And in many cases, I think it's worth pointing out, don't be too scared. It doesn't really matter. Like the things that matter, I'll show you an inside compute afterwards, like looking at the stores for these instructions. In fact, maybe this will be a better, can everyone see my inside compute now?
Yeah,
I
it's
assume
a
it's much
it's
too
a tad
small though.
it's small, yes.
Yeah, does anyone know to increase the size in the... I'm not sure I've got a good way of doing it actually. Yeah, I've never had to increase the size. That is...
Yeah, like I'm on the NVIDIA forums. The solution is you can try adjusting the resolution of your screen.
Right. Okay, I'm not going to do that during Zoom because that would be a bit probably cause other problems. Um, I mean, I guess I could like take a screenshot and then zoom on the screenshot, right? But that's probably a terrible idea. Do I
Can you
TF
show
it?
just the SAS instead of SAS and code side by side? Maybe that increases the size.
Yeah, I don't think it will. Yeah, it
Okay,
doesn't
no,
change the
doesn't.
actual thing. That's yeah. Okay, I didn't think of that problem with inside compute. That's going to be interesting for other things. I guess I can do more things in Godbolt and directly in the code. What I wanted to show there is for each instruction, you have the warp
I
zone
think Inside
sampled.
Compute gives you the option to directly export as an image what it's currently showing. Maybe you can open that image
That
and
is a good
zoom
point.
in.
Yeah. Um, okay. To make sure to make it an easier folder. Okay. It's such an unexpected, interesting problem to have. That was not in my bingo card for today. But yes, that kind of works. Okay. Um, so for each instruction, you've got the store reasons. Again, well, no, I cannot go on it to kind of show you what the reasons are. So this is kind of your main debugging tool, and understanding the SAS helps you make sense of this at a much deeper level. And I'll get back to that later, at least assuming I actually have a good way of
So,
showing
so,
inside
so, so,
compute.
so, so Arun, in case it helps, again, we can post edit this and zoom in really, really
Sure,
hard.
sure.
So don't cut your flow too much. Maybe we can
Okay.
just
So I was going to go very quickly over these instructions to kind of give a baseline idea of all things work for people who've never read SAS. This is upper, so there's no like constant reads in regular instructions. Um, this is loading a constant. This one I think is kind of a driver related thing that's not actually used for anything else. This is loading a special register, which is the thread ID. So it's this. It needs to load that from a special place in the SM to know what thread is currently running. Same for the workgroup ID. And then it has to take this and multiply it with, I think that's the actual thread group size. That's a good way to show that the compiler doesn't know at compile time for either the PTX or the SAS what the actual thread group size is. So it has to compile the shader in such a way that it works for any thread group size from 32 to 1024, and it cannot optimize around it. So here it's effectively doing this is integer multiply add, which effectively does this computation. And the really nice thing in Godbolt, which is actually nicer than inside compute to some extent, is, well, it's kind of the same. It's much nicer than NVIDIA's has and slightly quicker in terms of response time inside compute in my experience. It's just looking at the correlation between the source lines and the SAS. You can also do that in PTX. One thing you cannot do in Godbolt is go like between PTX and SAS, which you can do in inside compute. Um, there there is a third way of looking at assembly, which is using the QOps dump and NVIDIA disassembly tools from NVIDIA. So there is an official disassembler from NVIDIA, but no official assembler. And if I take cursor, SAS line info. Yep. So unfortunately, the way it works when looking at SAS in that's been generated by that with the line information, as far as I know, the only thing it will ever do is kind of give you the line number in the file, and then you have to manually correlate it. So in that way, both Godbolt and NSAT Computer are a much nicer way to kind of do that correlation. The other thing I was going to show is that actually makes it much easier to understand what's happening in this program, especially in this case, is, let's see if I can make this smaller. So maybe I just need to accept I'm only going to have one thing. Actually, that is kind of exactly the right size. It's fine. So both in Inside Compute and as an option for NVDisasm, you can get the live range and all of the accesses for every single register. So something that's worth pointing out is the register allocation happens in PTX AS. So in PTX, there are no real register numbers. It doesn't tell you anything about how many registers the thing will actually take in the end. The actual registers are allocated based on a very complex algorithm, most likely to avoid bank conflicts, minimize the total number of registers over time, and so on. So you should make any kind of importance to what the actual number is. In theory, in terms of bank conflicts, there's two banks, so even registers will conflict with other even registers. But so for example, in this case, you can see R2 and R7, which would be the two, one is the even bank, one is the odd bank. So the compiler probably intentionally allocated registers such that they would meet a bank conflict. But NVIDIA's hardware bank conflict resolution is actually really good. So compared to some architectures, the cost, if it doesn't manage to do that, is quite low. And it's one of those things that you typically don't have to care about. I mean, especially in the sense that there's nothing you can do unless you draw the SAS yourself with an assembler. And the compiler usually does a very good job of it. So this thing over here is really useful to kind of understand what the dependencies are and how things are working. This is showing a register write. This is showing a register read. And the X means that it's both reading and writing that register. So something that you can immediately see here is some instructions will write multiple consecutive registers. This is writing R2, but it's a 64-bit instruction. Registers are always 32-bit in NVIDIA GPUs without any exception. So you end up writing R2 and R3. There is actually, where's the I'm at? Oh, that's not the same shader. So if I go back to my shader here with this I'm at white is actually another example of a 64-bit instruction, because even though the registers are 32-bit, the addresses for memory are 64-bit. And so as far as I know, this instruction actually is kind of microcode and ends up working as taking two cycles and writing two consecutive registers, R4 and R5, over two cycles. Yeah, so that's, let me see, is it easier? Yeah, so in terms of the liveness information, you can get the same thing in Inside Compute. You cannot get in Godbolt, as far as I know, which is another kind of, I think a theme here is all of these tools have different advantages and disadvantages in terms of looking at the SAS. Inside Compute, if you're actually doing profiling, is obviously the best because it gives you real information. In terms of iteration speed, Godbolt is probably the best. But then there are upsides to just looking at the SAS this way, and it's kind of, if you're running, so for example, ALM.C, we got it configured so that on every single integration, we get the SAS for all the kernels dumped. So even you don't need to run it, it does run as part of integration, but in theory, you can get the kernels just from compilation. Because the typical way that CUDA kernel compilation works, but there's another way, is that when you do the NVCC, it will embed the PTX and the SAS inside the binary. So you just need to run qops dump, which is documented on that page, in order to get it out of the binary. there's also the CUDA driver API. Typically, people use the CUDA runtime API. I mean, I assume something like PyTorch probably uses driver, but simple programs use the runtime API. And the driver API lets you load a Cubin file with SASS directly or load PTX directly. So it's not part of the binary. It's effectively something that happens and then the compilation happens at runtime.
Can I ask a
Yep,
question?
go on.
Can we just watch you firsthand compile a kernel and open it and then say compute, like what your normal flow is for that?
So, okay, so my normal flow actually is something I've kind of changed over the last week in order to kind of optimize my iteration time. So what I've worked on the last week, and I had something similar but not as good before, and I would like to open source this once I've cleaned it up. So I've got a script that effectively watches a directory and runs, let me see if I can open cursor. So it will end up running like this script every single time whenever there's any change in that directory. So this is a command that will end up running NCU on the server and writing a profile to the server, a profile.ncu rep file. I've got a bunch of other options there, which the most important one is set full and import source yes. And then after that, you've got the actual command, which in this case is this, which is the way my framework works at the moment. And then on top of that, I've got it outputting the disassembly. So this framework uses the driver API. So it compiles the shader at runtime and outputs a Cubin file, and then using vdisasm to write it to a bunch of files like these ones. So what that does, if I take these, so it should be that if I take this one and just, let's see, put that there, just update it, this then runs automatically. Let's see, which one is this running then? Work in progress. Okay, I don't really want that. I would like this one instead, which is my simple value shader. So this is the file of the kernel that's going to be running. It's generated all of the SASS file locally on the server. And then I made another script that will download this to, so this is running on my local Mac. It will download this to SCP and then open inside compute with that file. So let me make sure that's the correct one. I think that's right. And then, yeah, that's it. So it was on the other desktop, but it's opened automatically once I press that. So it's a really, really quick flow to run NCU on the server, grab the file locally, and run it in inside compute. The alternative is to use start activity and kind of do it like that. But yeah, I think that's kind of as downsides and upsides. I kind of prefer my flow for that. Does that make sense?
Yeah, it does. Thank you. So I'd love to see that, like get that code when you're ready to share
Yeah,
it.
it's one of those many things I kind of want to clean up. I just have at some point accept the fact that it's useful to people, even if it's not as good as I'd like it to be. But I'll pass it through like one iteration of asking Claude to make the code better, and maybe that's enough.
Awesome. Thanks so much.
And yeah, I kind of developed this partly so I can do live coding for this presentation, because this kind of allows me to change something very quickly and show that to you in inside compute, except for the fact that I didn't plan that inside compute is too small. So using Godbolt, going through those instructions. So this is loading a constant, this constant in this case here. You can see by highlighting this, that this one is the block dimension, C0. It's loading the thread group size, the thread ID, the log dimensions, and then doing integer multiply add. Int is 32 bits, so it doesn't need to do the wide one. Whereas for the address calculations later, it needs to do that and write to both registers. It's loading some other constants. So all of the kernel parameters are passed through constant memory. It's worth pointing out there's a limit of 64 kilobytes or something like that. And yeah, 64 kilobytes for constant memory. But I think there's actually two separate limits, one for the kernel arguments and one for everything else. Like it's kind of all of this mess is a legacy of the way direct extend worked back when G80 was designed in 2006. Like the 64K is just what Microsoft put in direct extend back in 2005. It hasn't changed since. One thing when I'm kind of mentioned all the different architectures and the way it's different between Volta and other ones, the way constants work is completely different on AMD, like completely different, as well as branching is completely different. And without going into too much detail, like other GPUs also tend to handle this kind of thing very differently, and it's all very unique, but all kind of equivalent and can be emulated one on the other for things like ROCm and IP. So this is a pointer, which is a 4-byte constant in constant memory for the kernel argument that is then read by this instruction. This is the one for the output, and then it's doing an address calculation. I'm at white, so this is the destination registers. It's R2 and R3. R7 is the ID, which is what I calculated there. And then it's multiplying by 4 because it's a float, so it's 4 bytes per element. And then it's adding R2, which is that pointer that was loaded from a constant. And it's kind of interesting to see how that was different in Volta, where in Volta, you can see like those constant loads were part of the IMAT. And yeah, there's a couple of other differences. I've never really understood what this instruction is. It doesn't really matter. This is a good example of sometimes you look at SAS and there's things that just don't make sense. And you can kind of assume they are low-level hardware requirements. Potentially, in some cases, I think there was something with, was it TMA? Maybe it was something else where it didn't make any sense to me that the NVIDIA added a loop, kind of a spin lock, and it was, I suspect, just a hardware bug. And in many of these cases, the important thing is, well, for dynamic code, like that loop I just mentioned, that's not like this. This will always run. This will always take a cycle, and just the way the hardware works. For those kind of loops, the key thing is using inside compute to see whether those instructions actually get executed. And in that case, that loop was not getting executed whatsoever. It was kind of a corner case that they had to handle, probably.
Yeah, maybe one thing to add here is that the compiler also can get very clever in using instructions for things that you wouldn't necessarily expect them to be. Like if you divide by a constant, that might end up like bit shifts and like a sequence of bit shifts and multiplications or whatever. So sometimes it doesn't make sense at first until you start really looking at things. And especially I've seen in my code like half like HFMA or something popping up without using any data type half, and I think it's just some weird thing that the same instruction can be used for other things.
I was planning to mention the HFMA thing later, so I might hopefully get back to that. I think I'm more or less done with this. I was just going to say this is the load. It knows it's from global memory. The descriptor thing here and the way that works is one of the difference in Opera, and one of the reasons why QAssembler doesn't work out of the box, as far as I remember. And then this is the actual thing doing the value max. Well, this one. And then it's storing the results. And then it's done. This is padding because programs always need to be a multiple of 256 bytes. So I think that's about it on this thing. Let's go to the next. Yep, let's go. That kind of covered this slide and other things as well. Right, I was going to show this. Yeah, so something I wanted to show in terms of understanding the mapping between PTX and SASS. Gosh, everything I've zoomed in so big that I literally have no idea what I'm looking at. Was it this? Yes, it was this. I can probably just copy paste it into Godbolts because, yeah, quicker. Yeah, there we go. So this is a fairly simple kernel loading data from, yeah, that was kind of all because of the way my framework does. For God, but it's easy if I remove it. So there's a very simple kernel just doing an add between two things in an array. Like it's not even using the thread ID, so there's fewer instructions. You don't need the S2R and the IMAD and so on. Obviously, it's not a real-world kernel you ever want to use. So it's loading two values from a constant memory using LDC. And then this is a PTX instruction that's inline PTX to do an addition. And so if you do output equals input plus dynamic int, it will literally be completely equivalent, and this will not change. The reason I wanted to show this is a very simple case of PTX is not a one-to-one mapping to SAS, is the instruction that actually executes integer addition in CUDA is R3. In some cases, we actually use the IMAD pipeline, but typically we use the 3-input integer addition instruction. And RZ is actually just a register that represents 0, so it's not a real register. And what this does is it writes to I5, adding R0 and uniform register 6, and then this input is not used. Now, if I increment the next line, that's a second addition with another input. I've got another load, but I don't actually have an extra addition instruction. I'm just reusing that empty operand that was not used previously. And if you look at the PTX guide, PTX ISA, in terms of addition, there is only an add two values instruction. So there is no way of using the 3-input addition automatically, manually. That's always something the compiler will do for you. And it's a very simple case, an example of something where obviously the line info mapping also cannot really work. So if I look at this, it says that this instruction is caused by this, but really it's caused by multiple things. And the way the line mapping works is it assumes things are one-to-one, which it's not, and that's one of the many, many reasons why it's not always accurate. There's also kind of another interesting case there is something that doesn't work the way you kind of expect in hardware is logical operations like AND, OR, XOR, and so on. If I go there, so I'm going to do XOR. So it's using this lob3 instruction, which you will see a lot in anything that does like bit operations. And yeah, I'm not going to go to the instruction. There's some documentation somewhere you can find that people have kind of mapped the way. Well, I think there's actually a forum post by Robert Corella about this from NVIDIA. But effectively, this is able to merge multiple bitwise operations into one. And in some cases, this actually can merge like way more than 3 because of the way simplification works. And the compiler will try to figure that out. But obviously, it's using heuristics because it's kind of a very complex problem to get it right for like really long chains. That's kind of so you kind of need a full SAT solver for it. But again, in this case, this is kind of the compiler will automatically turn. Let's see, moving this. Sorry, the Zoom thing is in my way. So it will automatically turn these PTX instructions or the CUDA equivalent into log3, but you can also use it directly. And so it depends a lot what's actually available in PTX, how that maps to SAS. And just like the only thing that we say is it's absolutely not one-to-one. Right.
Maybe one more question about your example. I'm never quite sure, like, do you actually need ASM volatile or is ASM enough in this case?
So the volatile, it's documented in, let me see, the inline PTX page. Maybe easier if I've got it open, it's easier if I just search it. Inline PTX assembly in CUDA. It's related to memory, if I remember correctly. So yeah, it's related to optimization and automatic code removal if something is not used. It's like this side, for example, there might be a side effect. I guess a good example might be, I'm just kind of curious now whether that will work. So if I do the other reason I kind of keep mentioning like dot is great. The one thing that is not great is there's no copilot, there's no cursor, and it just reminds me of how much I've forgotten about basic things. So I think I want to do nanosleep 0. I think that's the one. So nanosleep is kind of an interesting instruction that's also useful for things like spin locks. It is available both in PTX and in CUDA. You can actually expose directly in CUDA as far as I remember. So it will sleep a given thread for a specified number of nanoseconds, not cycles. It's actually converted in the hardware to cycles. And it may be a dynamic value or an immediate fixed value. And it's approximate, obviously, it's not an exact duration. So yes, this is it. So if I do it without the volatile, does it keep it? Maybe it's smart enough to realize that, yeah, it's smart enough to realize it has to keep it. But in theory, it's for that kind of thing that you want the volatile. I'm trying to think if there's any reason not to have it. There's also this one, which is kind of important, which is effective, which I've got a slide that's kind of related to that after this, which is how do you change your program so that your SAS kind of fits together. I'm kind of checking on time. Okay, I think this is taking a bit longer than I expected, so I might just move on to some of the microarchitecture stuff and then come back to this.
You don't have a hard stop, by the way. It's totally
Sure.
up to you.
Sure, but I mean, I also feel like the microarchitecture stuff is kind of important, and unless I eventually move on to that, I will just spend all of my time doing live demo of this. But yeah, in terms of the pages that are important to be able to work in PTX and SAS, I would say like the PTX ISA, the inline PTX assembly, the CUDA binary utilities, and obviously the CUDA C++ guides. And there is something in the CUDA C++ guide that's really important that I'll get back to afterwards. Right, so I think that's, yes, I was going to show the A100 reduction. I've got this in cursor. I had it open. So if I just take this. So this is to highlight a new instruction that was added in Ampere. So this needs to be out, out, and I think that's it. So this is something that is not actually directly available in the CUDA API. You can use cooperative groups or trust or CUP, I think, to effectively end up using it automatically. But you cannot, as far as I remember, call this instruction directly in CUDA C++ without using inline PTX. And what this instruction does is it does a reduction across the 32 elements of the warp. So it will take the maximum value of those 32 threads and place it in every thread. All of this is documented in, no, wrong page, in the PTX manual really well. Always kind of the complexities with the member mask and other things. That's, yeah, let's just pretend those don't exist for the time being. The quick kind of tip I wanted to give here is obviously abs max is kind of an important thing for scaling tensors for FP8 and other contexts. You can actually just assume that a floating point value is equivalent to a 32-bit unsigned integer. No, sorry, a 32-bit sign. No, right. So if you're doing effectively in if you're doing fapps first of this, is it fapps? I have no idea. Good example of being too used to copilot. If you do this, then you can effectively just act as if it was an integer, despite it actually being a float, because the ordering is the same. Like a bigger integer will be a bigger float if you look at for absolute values. There is a trick to do it with 2 instructions for the non-absolute max case as well, but it's a bit more complicated. The reason why that matters is those reductions only exist in the hardware for integers. So if you're doing a floating point reduction, you still have to use the shuffle instructions and kind of do multiple steps of shuffling. Whereas this, if you can use it, is way quicker and way lower latency. Okay, going back to the presentation. Okay, I'm not going to show the 800 int4 matrix multiplication case, but that's kind of an interesting example of a like extreme case where the PTX and SASS don't match and where forward compatibility is tricky. So Ampere introduced 4-bit matrix multiplication. Hopper added FP8, but actually removed int4 for whatever reason, like just didn't think it was worth the hardware engineering verification time. And so, but the PTX instruction still has to be supported, because the way CUDA works, the way PTX works is if it's in, it stays in forever. So what the PTX as does is convert that into a very, very large number of 32-bit instructions and other things that will be incredibly slow. So like it will be way, way, way slower than the int8 matrix multiplication. And unless you look at the SAS, you don't really know that, right? So it's a good example of forward compatibility and PTX kind of just being a PTX AS basically being a black box, and looking at the SAS be kind of important to make sure the black box is doing what you want it to do. But all of this is kind of a good thing, because if we didn't kind of have this whole JIT approach to compiling GPU codes, we'd have the same mess that x86 has. And I think the G80 instruction set was interesting, like it's got some really cool parts to it, but if we had to be stuck with the G80 instruction set from 2006, like I think we'd lose a lot of efficiency. So this is okay. So I want to try to see if I can do this part really quickly. A big problem, a big problem when using SAS is for a complex program, you end up having kind of things optimized long distance and moved around by the compiler, and you have no idea why this thing there is doing that, and the source line matching doesn't really always work for the specific instructions. You don't know where it's coming from, etc. You can kind of mitigate that through a couple of tricks, and there may be extra tricks that I don't know of, because these are mostly things that I figured out myself. So kernel value. Do I have this here? Maybe not. Maybe I need to very quickly write it. Let's see. Yes, I think no. Okay, screw it. I will write it in as little time as possible. So another interesting point that's worth highlighting is there is like when you do arrays in CUDA, you have to be it's both very powerful in terms of actually forcing the compiler to do some optimizations, but if the compiler cannot do those optimizations, it can be really bad. So let's take this. So if you do a for loop with any kind of fully static number of iteration counts, and you're using the loop counter as using the loop counter as an index, reading or writing an array. What you will actually end up getting, let's see, is this correct? Sum did okay. It should be correct. What have I done? Oh, n. And then, yeah, SM9. What have I done? Oh, yeah, okay. So, okay, that's actually kind of interesting as well. Let's do that. So let's do data n equals n. So the first loop is loading from global memory into this array, and this then does a sum. Okay, again, it's not meant to be a representative program. It's just to highlight what's happening. Okay, perfect. It's doing exactly what I wanted to do. So each of those loads, this is loading one of those floats, a 32-bit loads, into a single register. And then the sums are these f-ats. And you can see what a compiler tries to do, partly to minimize register pressure, partly to kind of balance the pipelines and the bottlenecks, is it will do like a large number of loads to start with to kind of maximize the amount of memory and instruction level parallelism. And then it will kind of interleave those ats across the loads. In some cases, and this is actually something where that register liveness and access thing I showed, you can get for NVIDIA's ASM inside compute is really useful because it's kind of sometimes hard to kind of track what the real dependencies are. Yeah, so this effectively, makes it quite tricky to figure out what's going on in more complex cases. And ideally, you kind of want a way to separate things. So to prevent the compiler from doing clever optimizations across a certain area. Another example of this is if I did fid less than dynamic return, and I did this here, the compiler will realize that, well, that means I'm not actually doing anything with any side effects. And it's going to end up moving this to the very top. So this is the test and the exit. Yeah, so one way of doing this is adding certain kinds of instructions that the compiler ends up having like kind of seeing as like separating the basic blocks. So nanosleep should be one of them. Did I? Yeah. Oh yeah, put it in the wrong spot. I should put it between the two loops. So this is one case where it's kind of really tricky to make it do the right thing. And I'll show you a trick that I think should work for this. That is not working. Interesting. I might have to resort to my crazier trick. Something else that's really kind of interesting there is launch bounds. So this is kind of to do the opposite. Well, check if this is correct. Yeah, okay. So this is block, C256, 8. That should work. Yeah. So this is compiling, assuming there's like I occupancy. This is asking it to have 8 blocks of 256. Compile the shader in such a way that the number of registers used is low enough that you can fit 8 blocks of 256 of 248 threads on each SM. But if I make this 1, it knows there is access to more registers, and it ends up changing the way it's compiled and doing all of the loads first because it assumes that's actually better for performance, and all of the f-ats afterwards. So the reason why things were kind of interleaved in that weird specific way is because the compiler was trying to stay below like a certain kind of number of registers. I think it seems to be using 28 registers, so it's at 0. In practice, it could have used more, but these are all heuristics. The compiler doesn't really know all the compile and register location will end up after some stages of compilation. So it's kind of sometimes being too conservative here. It's trying to stay below 32 registers, which is what you need for maximum occupancy on Hopper. Now, there is another crazy way that I wanted to very quickly show that I discovered in order to this. If you use a no inline device function, and let's say it's doing float x, float, return x 0f, and then I do not inlined something like that. The details don't really matter. So, okay, no, actually, that is a terrible case because this is actually showing something else that's kind of interesting. Is yeah, this is. Oh,
I think
that's
you need
because
to
we
decrease
looked
the
at
launch
case
bounds
spinning.
again, and then it works.
Yes, exactly. Like I think it's kind of because there's multiple things that can happen here. Yeah, so this is the launch bounds, and this was a case where because of the launch bounds, it's forced to try to use register spilling, which is going to be really slow, which is STL and LDL. So if you see STL and LDL in the shader, in the SASS, that's a really bad sign. And you just kind of look at things like launch bounds and trying to reorder things so that register pressure goes down. In some cases, the tiny amount of spilling is not necessarily a bad thing compared to lower occupancy, but typically it's really bad.
Do you mind elaborating on the forcing spilling point? What does that mean exactly?
So this, okay, it's not forcing spilling, it's forcing compilation such that you can fit 248 threads per SM, which means you can you need 32 registers or less per thread. And because of the way this shader is written, it's not able to compile below 32 threads by reordering operations. And so the compiler is forced to spill to the stack into which effectively use DL1 and potentially DL2. That makes sense?
Yeah.
Yeah, so the trick I wanted to show here, let me use it to 16 so it doesn't hit that problem. And maybe to the launch bounds. So that should work. Yeah, so here, by having this function call there, which ends up calling this function, it's effectively, this is one of the strongest things I found. I'd be very curious if people know of other even stronger ways to kind of force the compiler not to optimize across a certain boundary. But this seems to be like a pretty powerful way to prevent optimization between this and this. However, like a lot of this is related to like memory and assuming that memory might change between those points. There are things the compiler will still do. This branch here of it's still moving it to the top of the kernel and doing an early exit. So it's not perfect.
I think maybe slightly cleaner way of doing this is just having an assembly statement that claims to clobber memory and doesn't do anything.
Yeah, so that's something I've also tried. I think there was a case I saw where this actually worked and the clobbering didn't work. But yeah, typically the clobbering is the easier approach, which would be like as volatile with that memory flag. Okay, anyway, I feel
And
like
maybe one thing to add here in terms of optimization is also that if you're not careful, you can do exactly this thing unintentionally quite easily. If you're writing to memory and the compiler can't figure out that you're writing to memory that's distinct from what you're reading, then sometimes it cannot optimize.
Yes.
Yeah, maybe. Yeah.
Yeah, absolutely. So if I just did, yeah, so that's why you need, not going to have time to go into that, probably like the const restrict for your arguments. And that's a whole other topic, which is, you can Google that and figure out why it's important. So I think I've got quite a bit to cover in terms of microarchitecture, so I'm going to go back to the presentation now. Hopefully that kind of made sense. Right, so, okay, that's another live demo. I might just missed most of that because I wanted to try and go to do it at the end if I've got time. So Volta CMT is kind of very different from the way previous NVIDIA GPUs work, the way AMD GPUs work, and the way other, like effectively, there's so many different variants of CMT, and Volta's one is quite unique. Actually, let me do a very quick live thing here. So if I do if 16 should give me what I want. Oh, 4.0. And it's kind of, again, I like just, oh, nice, like something like Godbolt that you iterate incredibly quickly is. Like if I had to wait like 10 minutes towards compile to get this SASS and then iterate on that, I would just give up instantly. But obviously you can, yeah, depending, I don't know what the flows are in some other case, but there's probably always a way of getting faster iteration time than just going to the whole framework. So yeah, so the way branching works on NVIDIA, let's see if I've got right. Okay, no, that's too. If I move some more stuff there, that will probably work better. Okay. There we go. So now I've got two different branches. This is. And so predicate registers are what's used for tests. They are per thread. There's also uniform predicate registers that are per warp, which are much more rarely used. This is testing whether this value is greater or equal to this value. That's an immediate register. And then writing to P0. And then this branch is saying if P0 is false, then branch to this label, which will be here. So the thing that's kind of unique about Volta CMT is, so if you look at this diagram there that they've got, effectively, that's my actual diagram is a bit misleading. All of those, the threads that take the branch will run, and it will actually go all the way. Those threads that do run, there is another, what is it? Okay, so that's actually interesting. This is a case where there's two exit statements because it knows that there's nothing to do afterwards. If I do that, then that will certainly change what it looks like. Because I want to get a B-sync instruction. No. Equals sum. Okay, I need to do this. This is all the fun of doing this live, but hopefully it's not too bad given the quick iteration times. And kind of shows the way you would do it yourself, hopefully. Perfect, I think. Yes, perfect. So this branch, if it's not running this path, then it branches to this label here. And then after that, yeah, okay, that confuses things. But after that, it will end up branching. So okay, let me start over. This will be much clearer. The way the warp works, all threads are active. Then now all the threads that fail this branch are disabled. So the threads that would branch are disabled. The threads that do not branch execute this, and then they branch here to this label at the end, and they then run the B-sync instruction. what the bsync instruction does is the threads that are active get disabled, and the ones that were disabled, which in this case would be the ones that did take the branch, then I re-enabled at this label point. And then all the threads of the other side of the warp that took the other side of the branch will execute this. So there's really like a program counter per thread that is actually written in R0 and R1 that may actually take 2 of your registers for the program, and you will actually lose 2 registers that really you've got 30 registers rather than 32. Okay, did that make sense? I'm realizing this is quite a tricky thing to explain without a lot more background. But fundamentally, the key instructions you have to care about are the set P, the bra, and the bsync. And the bsync is the convergence points. So the number of instructions required in this case for that the if else is 1 for the set P, 2, 3 for the branches. There's 1 here, 2 for the branch, and 1 for the bsync. So there's 4 instructions.
What's the BSSY? That also looks like it.
This one.
No, in the beginning, like directly in front of the branch, there's one more instruction that also
Oh,
has
right.
this label.
Okay, yes. This initializes the barrier. So it's basically, I mean, yeah, the hardware doesn't do it for you. You have to kind of say, and this is one of those things that I only understood looking to NVK discussions about how the barrier registers works, and it's kind of messy. So yeah, that's a good point. That's another instruction that will practically always come before dynamic branch after the set P. Okay, if you get any questions about that, let me know. This is just, it's easy if I explain in 10 seconds what I was trying to get to here by showing the register dependencies. So this is kind of an abstraction, assuming that the hardware and the instruction set can support representing this exactly, which may not be possible, but because it doesn't even have barriers, or because there's loops and other complex control flow that make this tricky. But this kind of looks as if it works on a CPU where the hardware is tracking the registers, and a CPU will automatically figure out that there's a dependency between this instruction and that one and do the stalling completely dynamically. The way it works since Kepler is that's not the case. The instruction itself will encode the way the dependencies work. So there's still a bit of hardware for tracking things, but it's a lot less. And all of the long dependency instructions will have a write barrier, which is when the data for like a load comes back, and a read barrier, which might be when the address register where the address is stored for the load is freed up. So that happens much earlier than the actual data coming back. And the barrier mask is making you wait for those barriers to be satisfied. So if it's set on an instruction, that instruction cannot execute until the previous instructions that incremented those barriers are fully finished executing. The stalls is the mechanism for arithmetic instructions like FMAs and integer addition and so on, which is more of a fixed number of cycles, which the compiler has to figure out when is the best case that it could possibly execute. So there's actually kind of a few interesting corner cases because it's not per instruction, but where it's not actually as perfect as hardware. But for all intents and purposes, it's very clean, very simple. The key thing you realize with this instruction set is it is very clean and simple compared to most CPU and other GPUs. It's a fixed 128-bit fixed instruction length, which is probably the lowest code density of any GPU I'm familiar with. And NVIDIA compensates for that with incredibly aggressive prefetching from my testing. So if you've got loads of crazy branching and conditional code and like warps running different paths, which is the case for ray tracing, for example, the architecture is actually not great. because they kind of prefetch things they don't need and then end up missing more often because the code density is low and so on. But for machine learning stuff, where you effectively don't have that much kind of crazy branching, and it's mostly straight line, it's actually really efficient and kind of simplifies other parts of both the hardware and the software. And if you actually want to look at the lowest detail, and NVISA solver is really quite nice. This is the kind of an aside saying that a lot of information you'll find online is very subtly wrong, and it's kind of impossible as a third party to get most of the details right. So the Volta dissected paper, for example, is wrong about the size of the instruction caches, or more specifically, which is DL1, which is DL0, and so on. And like actually there is a 3 kilobytes L0 per SM partition. But again, most of these things you don't actually have to care about. The best source in lots of cases is actually NVIDIA's performance forums. So both Robert Covella and Greg are very active on this, and they've answered lots of questions. And there's lots of like other really smart people, not gonna give names, but that post on loads and loads of threads. And so if you're looking for a problem, often the search on those forums will be quite helpful. And Greg, especially for like performance counters, will give lots of detailed answers, like the way L1 bank clashes work and so on, that is not actually available elsewhere. And it's kind of a really good gold mine of information. And obviously that gold mine has been created because people pose questions and they give answers. So I think I tend to just read and find the information by searching it because there's so much. But in some cases, just pose the question, and I think it's a really great resource that other GPU vendors don't have. Like, there's nothing anywhere near as active as that product I know for AMD or Intel or Apple, and it's a really great resource. So trying to dig deep into the actual microarchitecture, NVIDIA has been kind of focusing more and more on the system level in their presentations. So, for example, the Blackwell hot chips presentation basically tells us nothing about the ESM architecture or anything like that. You can kind of go a little bit into detail of what the ESM looks like from some of the public diagrams, but you kind of want to go a lot deeper than this. You don't want to go too deep though. So this is the data path circuits that NVIDIA generates with artificial intelligence as opposed to classic EDA tools. But this level of abstraction tells you nothing. There is some very low level, like data path specifications can be hundreds of pages long, really complex, kind of, oh, do you implement the specific IE754 thing in the right way that's efficient? But that's the wrong level of abstraction. So in terms of publicly available resource, the Volta and Turing hot chips presentation are probably the best we have that's official from NVIDIA. And again, you kind of really want to combine that with micro benchmarks, and some of those micro benchmarks don't exist and take a lot of time to create, but it is what it is. So this representation, you can see here, there's 4 partitions, 4 subcores per SM. This is important when you write CUDA code because of the way register allocation works. It's not really 64 warps. It's really 4 sets of 16, which is also exposed directly for warp groups and upper tensor cores. And so the registers are actually allocated in chunks of 8. And there's specific thresholds where if you go from 56 to 64, you actually lose some occupancy, and I think 64 to 72 you don't, and other kind of other way around, kind of other weird things like that, which are a consequence of actually like being very coarse granularity, because it's kind of just multiples of 16 rather than 64. So except for the L1 and the shared memory, which is kind of really per SM, most things, and the TMA now, most things are really per partition. And it's kind of the level of abstraction that you sometimes want to think about. This diagram is kind of showing, there's multiple pipelines. This is kind of a very, actually not very correct abstraction based on what has been said by the performance tool guidelines and kind of other things about how this really works. But at the eye level, the really important bottleneck is that the warp scheduler per partition can only schedule 1 instruction per clock. And there's now in new architectures 2 FP32 pipelines, but effectively you've got a set of pipelines, and you've also got like things like branch instructions. Each of those pipelines has a maximum of 16 threads per clock. So for a full warp of 32, will take 2 cycles to execute. But that means effectively you can only keep 2 pipelines fully occupied. If you've got loads of integer instructions, NFP32 and branches, the bottleneck might actually just end up being the decode fetch schedule rate of 1 warp instruction per clock per partition, which is 4 per SM. So the Turing output presentation kind of highlighted before the consumer ampere. So this diagram is still correct for A100. They effectively add an integer pipe, an FP32 pipe, but the integer pipe isn't really just doing integer stuff. It's also doing floating point min max, compare, and other instructions. While the FP32 pipe here is actually also responsible for integer 32-bit multiplication instructions like IMAT. So those names are very misleading. And on newer architectures, what they've basically done is they've added a separate FP32 only pipe called FMA Lite. So there's still the same FP32 pipe that can do integer multiplication. There's another pipe that can only do FP32 multiply add, fuse multiply add. And then there's the existing integer pipe that will do integer, floating point min max, and so on. And then MUFU is the special function for things like reciprocal, square root, sinus, 10H, and so on. But again, you only got 1 warp instruction per clock scheduled. So you can only use, well, you can only, of the full speed pipelines like FP2 and INT, you can only use 2 of those pipes at full efficiency. Potentially, you still get like bank conflicts and other things that mean you don't get full performance. Like when you think about like the speed of light, you'll never get 100% because there's loads of low-level bottlenecks. But depending on the case, the warp schedule will be the bottleneck. Another thing that's interesting to point out there at the eye level is the trend in upper has been to do bigger instructions that do more automatically outside of DSM and regular instructions. So a TMA instruction will do a huge amount of work in what's, in theory, a single SAS instruction. In practice, there's a whole bunch of override before and after. Same thing for upper tensor cores, like one instruction will take many cycles. And so they're effectively avoiding this warp scheduler bottleneck by having bigger instructions that do more work. But if you're running vector workloads, that bottleneck is still really like non-tensor core workloads. That bottleneck is kind of important in my experience. So we kind of implicitly touch on uniform registers as part of looking at the SAS. Don't think there's a lot of extra thing there to say. It's obviously a power benefit. It's not as much of a performance benefit in my experience, partly because of that 1 instruction per clock bottleneck. Like I think, as far as I understand it, that's something like DLDC instruction here that loads a constant into a uniform register, even though it's not really using most of the resource of the SM, like the register file, it still takes a scheduler cycle, I think. So I've mentioned barriers a few times, like including in the instruction encoding, but it's very confusing because it actually means a bunch of different synchronization systems that are implemented differently in the hardware or may have different kind of things in the specification. And this is just to highlight, I'm not going to actually explain this properly now, like don't assume just because something is a barrier, that's actually the same thing. So barrier instructions for thread group sync fence, sync threads when you synchronize an entire thread group is a barrier, but that's completely different from the dependency barriers I mentioned, completely different from like TMA barriers and so on. So this is one resource that's kind of put in a weird place in my opinion, but it's like incredibly useful, is 541 arithmetic instruction throughputs. So that's kind of NVIDIA's official documentation of what different throughput or different pipelines is across generations. Some of it is like non-obvious, like for example, population count for pub count is like changed weirdly over generations. So it's a really good reference, and you can see like 64-bit is not supported on the consumer GPU, it's at high performance, and so on. What this doesn't tell you is, oh, does this add up? What can you co-issue and so on? Again, I think in many cases it doesn't matter too much. Like we know that we've made the DX2 FPT2 pipe on consumer Ampere and Opera, the one instruction backlog bottleneck is probably more important. So this was going to try showing the warp scheduling dependencies in Inside Compute. Given Inside Compute is way too tiny, I think I'm just going to skip this. And yeah, it will take way too long to do properly. There is really good documentation that maybe I should just point out where it is. There is the provider documentation from NVIDIA. Okay, I don't actually have it open. That's annoying. Okay, I'll link it after the fact. I've got an appendix that I need to add a bunch of things to of the actual PowerPoint presentation that I'll add this to afterwards. The FP16 thing was just kind of an interesting side note. Like Eric mentioned, HFMA instructions being in weird places. I could try to quickly find it in live demo, but it's not that interesting. There are instructions that sometimes NVIDIA is using some of those other pipelines to do something like a move that just copies a register, because that's the pipeline that's free on that cycle, or for some reason it's actually the more efficient pipeline to do it on power-wise or whatever. So you will sometimes see some instruction that basically just do a copy of writing 0 to a register that have very weird encodings. And yeah, it's kind of, once you know what to look at for, it's very easy to kind of just realize that's what it is. So this is kind of a side note that's really important to think about performance analysis. NVIDIA really likes talking about Little's law, and I think it's a very good high-level concept. It comes originally from like industrial kind of modeling of rates of factories and things like that. In order to hide the latency of when in factory or escalator, like the length of the supply chain, you need a certain amount of things happening in parallel in order to be able to hide latency and achieve the peak throughput. So the implication is if you want a throughput of, let's say, 1 output every 10 cycles, and the latency is 400 cycles, you need a minimum of 40 threads or 40 warps to be running in parallel. Otherwise, it doesn't matter what you're doing, you will not be able to handle latency and you will run at lower performance. The key thing that is kind of relevant as part of thinking about SASS is it's not just about thread level parallelism. It's not just about occupancy and warps. It's also about the amount of instruction level parallelism and how many loads happen in parallel in the kernel. So this is kind of a simple example from one of NVIDIA's presentations for GTC this year. Something else that I think people often don't realize as a corollary is that because it's effectively sampling randomly, I mean, obviously, the schedulers are very complex. It's actually sometimes there's weird behaviors. That means it's not random, but you can kind of, at the first approximation, assume that what a warp or what a thread group at least is where it is in the program. Like on the right, is it like at the first load or is it doing the final store? It's kind of random, as depending like if you take the full latency of the program, the probability of being in that part is roughly the latency of that part of the program. And therefore, sometimes you're just going to get unlucky. You might have more threads doing the part that has less instruction level parallelism at the same time, and then you don't manage to keep your GPU busy. This seems like it's less of a problem because there's so many threads, but actually, like the way memory works is it's split in like SBM is 16 subchannels. So in total, you've got, I think, 96 subchannels on the H100. And those kind of all need to be fed like with things to do independently. And therefore, you actually need in order to get like that last bit of performance, like that last 1 or 2 or 3%, the fact that you sometimes get unlucky is kind of important, which is why you need like kind of a bit of slack and kind of have more latency tolerance, more instruction level parallels, more thread level parallels than you theoretically expect in order to hit the absolute peak. Yeah, this is all stuff that I'm not going to have time to do in much detail. I wanted to still probably go through the Mafutane thing for Gelu, and then very, very quickly the L2 side of where memcopy stuff I've been working on. Like I did that about 2 months ago or something, and I haven't published it yet, but I think it's really interesting. So the Mafutane and Gelu, this is another good example of something I want to use Inside Compute for. But I've got the LLM.C. This is the current BF16 LLM.C out of the box. And if I look at the Gelu kernel, the default is actually DRAM throughput 35%, compute 87. Yeah, I think this stopped and we started recording, right? So yeah, I can try zooming in, but basically it's just like DRAM is really low, compute is really high. What's happening? And let me see if I can actually copy this part because it is kind of important.
I think there is actually a way to make it bigger if you go to preferences. I think you can try to
where?
Yeah, like
This one?
Yep, and then font and colors.
Oh.
And then code font.
Code font. Okay. Yeah, that's very promising. Let's see.
And then it will need to restart though.
Oh, I see. Okay. Oh, that might be annoying because I've got those. Not sure I've got those. Actually, that is fine. I've got it saved in that directory. Okay. Yeah. Okay, that's better. I could go even bigger, I guess. Let's see what the code looks like. Okay, do you want me to make it even bigger? Is that good enough for now?
It's good. I can finally read it. This is good.
Okay.
Cool.
So if you look at the Gelu kernel in LM.C, we've got most of the instructions from this line, which unfortunately is kind of multiple things in one, but the bulk of it is going to be that tanh function. And the interesting thing is the tanh. If you look at the PTX now, source in PTX. Okay. This is 2 hours that size. Okay. SASS. Right, okay. I'm just going to show you the SASS very quickly. What's happening is the tanh in here is implemented in a really slow way that is using exponential function and a reciprocal function in the special function unit. It's taking 2 special functions rather than 1 that you might expect if tanh was supported natively. And then it is doing a bunch of things, including a loop, to increase the accuracy. So the reason for this is that if you look at the CUDA specification, is it this one? Yeah. So if you look at the tanh, you can see that there's a very specific precision requirement, which might actually be defined by IE 754, I'm not entirely sure, of it has to be 2 ULP error over maximum over the entire range. And it's really tricky both in hardware and software to get it to like be that performance across the entire range. So you kind of end up having hardware that works most of the time, and then a bunch of software tricks that, including this loop here, that will, or branch, I'm not sure it's a loop, I forget, that end up being used to increase the accuracy of that further. And it's the same principle for like cosinus and sinus and other things. In some cases, there are native intrinsic functions for things like sinus and exponential and so on, that I think actually used automatically if you use fastmath, which I think is probably always the case for Torch and LLM.C as well. But the interesting thing is there is no such function for tanh. So there's nothing to help you tell CUDA, I don't need this level of accuracy. However, in PTX, there is a specific thing as part of the, there's a dedicated tanh proxy function, which has different precision requirements than a standard tanh as in C++ and CUDA, and therefore doesn't have to do any of that junk. So I don't have it open here, unfortunately. I might just very quickly try to find it on the lm.c repo. But effectively, you end up with only a single MUFU, and instead of the RCP and EX2, much simpler code. Okay, the other thing I can quickly highlight here is because of this loop, it's actually not able to move the operations to maximize the amount of memory level parallelism as well. So it's kind of bad for latency tolerance because it kind of encourages at least the compiler not to move things the right way. So it's like doubly bad. So the way to fix this was this old PR I had where files changed, where you change you have to use inline PTX. And this is an example of something you have to use inline PTX. There's no other option. And then it just works and you like more than double the performance. There's another very quick trick that was kind of interesting is in the original code, you've got this thing of C++. Effectively, you end up with a multiplication, an addition, and then a multiplication of these two things. So it's an fmul, an f_at, and an fmul. By reordering it this way and kind of adding the 0.5 times x twice, you end up with only an fmul and fma, so you save an instruction. And this is something the compiler cannot really do because floating point isn't like fully it's not commutative, and therefore it would slightly change the accuracy. I've worked on compilers for like mobile devices at Imagination that did do this kind of optimization, but I think typically CUDA tends to be quite strict with these things, and so you have to do these things yourself. And it's not really obvious. Like if I look, well, especially this line that's kind of should have been split out, it's not obvious that this thing will result in that problem. And looking at the SASS is kind of a nice way to find that out. Okay, I will not have the time to do that. Something else I want to very quickly mention is when you think about like the speed of light and the efficiency of DRAM, you cannot actually get to 100% of the DRAM. And an interesting effect that, I'm not really able time to explain why it matters and what optimization you can do with it, but if you've got a kernel that only reads from DRAM, you might be able to read 95% of the speed of light, or if it only writes from DRAM, be 95%. Whereas if you're doing a one-to-one read to write ratio, because there's some overhead in HBM for changing between reads and writes, you might only be able to reach 90%. So the speed of light often is like the theoretical limit, and there's loads of low-level bottlenecks like the DRAM, like bank conflicts for instructions and so on, that actually you don't really have any way of analyzing unless you look at like RTL hardware waves. And you just at some point have to assume that you're the best you can do within the constraints you have. So the last thing I wanted to go to, and I don't think I have the time to do it properly, is one kernel I've been working on recently is an L2 side-aware memcopy. So the NVIDIA L2 is split in two. And unfortunately, the only kind of good public information about this is this presentation from the same people who did the Volta white paper. Okay, that's annoying. Which kind of show you how like it switches every 4 kilobytes between the two L2 sites. So there's not really any way to kind of say, I want this piece of data to be on this side of the L2 or the other side, but you can. There we go. Yeah, that's the presentation. So it's the dissecting the Ampere GPU microarchitecture. So that's kind of, if you're interested in that kind of low-level detail, it's a very good presentation. It's showing, oh, there's a massive latency difference between the two sides. Like it's adding like 150 cycles even from L to it between the two sides. There's also the interesting thing that kind of wasting some of the L2 because data might be duplicated in both sides. And if you look at the addresses, I think maybe that's different for A100 and H100. They say 8 kilobytes granularity. It's actually 4 kilobytes on Opera. So what I've done is I've created a kernel, and the mapping is actually very predictable between pages. I've created a kernel that will end up at persistent threads, knowing based on DSM and the ID, and then a test to figure out what the latency is, knowing which side of the L2 it's on. And each SM is only responsible for a part of the memory that is on its own side of the GPU. So this requires it to be like read-write one-to-one. If it's not one-to-one, you couldn't do it for both reads and writes. In theory, you could do something crazy like this for like a tensor core matmul just for one of the two input matrices. It would be kind of interesting to get it to work. But what this gives me is on H200, it improves performance by 2%, which is not amazing, but it's kind of nice for a jelly kernel. For Mencopy, it's kind of the same performance. But then it actually reduces power from 490 watts to 435. So it's like a 11% power efficiency improvement, which is actually, well, quite a lot. Like, as we've seen, that's about 20 nuclear reactors. If you do it, obviously, JLU is only a tiny part of a kernel, and normally you do kernel fusion. But there are things where I think this would be kind of relevant. It's a good example, like a very kind of microarchitecture related, very low level thing that you can only do this kind of thing when you kind of start digging at this depth. And then, yeah, I think that's basically all I've got, at least of the things I've got time for. And if you've got questions, let me know.
All right, thank you so much, Arun. This was pretty sick. Like, I'm gonna start reading some maybe comments and questions from chat. Dongyo Ju's asking, how did you measure power? I don't think Insight Compute gives power stats.
Right, that's right. So Insight Compute by default, I'm still sharing, right? Insight Compute by default actually changed the clocks to the base clocks, which is something you also have to be careful about because that makes some of the data non-representative. So the way to measure power is just NVIDIA SMI. So I did it kind of brute force. There is this command line option, LMS, that just loops it, and we kind of just update the power there live. You can also write a script that passes this if you want to properly automate it. There are like NVML and is it NVML? Like there's some APIs from NVIDIA that means you can do it in your program. But a lot of these things, like including some of the performance counter stuff, there's not actually that much benefit from using these APIs, at least for most use cases. Like actually just using those tools and passing it as a separate thing tends to be easier.
Yeah, like I think another nuance is like most cloud vendors won't let you change these stats like at all. And so like I think for consumer cards, you can do whatever you want, but in data center, I think they'll keep the power low to avoid temperature spikes.
Yes, but I think I could be wrong, but I believe inside compute there is that option of setting to base clocks. So you cannot actually change the boost clock. You cannot say force the clock, but inside compute will still change the clock to something much lower than what you get in practice, and still kind of affects all of the data you see in inside compute by default. And there's both the command line thing and like in inside compute, there's clock control here. We can do base and none. So none means the clock is dynamic and kind of dependent on thermals and other things. But yeah, you cannot measure power in inside compute. And even if you could, you wouldn't want to because of the way the profiling works, kind of change the workload completely. You want to use NVIDIA SMI or other APIs to get that.
All right, thanks, Arun. Well, I don't see any other questions in chat, so thank you so much.
I could ask something more if
yes.
Like you didn't really talk that much about warp stalls, but that's kind of like the entire reason why we do this, right? To avoid warp stalls. And something I only found out very recently is that in the SASS view of Nsight Compute, there's actually like a tiny thing more, and then you can select like specific warp stalls and also switch between generic warp stalls and warp stalls where no instruction was issued or something. And now I'm wondering why you act like the default thing is to show warp stalls and not just warp stalls where you actually didn't do an instruction. Like it seems like those are actually the bad ones and the other ones you don't care about. Like, do you have any idea about that?
I don't. That's a good question for NVIDIA. Are you talking about this tiny thing there?
No, if you go to the navigate by thing and click on the small arrow down, like at the top
go
of
to what? This one?
where you can select like which column to highlight, right?
Column chooser?
Yeah, exactly. And there's also
Right.
warp stall sampling, not issued samples, right? And that's disabled by default. But like, which one do you think is the more important one to actually look at?
Interesting. I don't think it makes that much difference. No, I see what you mean. Like it's the case where was there something to execute on that cycle anyway, so it didn't matter that we had a stall from this warp.
Yes, exactly. Like does
Right.
seem not actually bad warp stalls. Like if we have enough
So-
parallelism, we don't really care.
So I decided not to comment so far, but I think this one I must comment now. So this scenario can happen when there is no resources that is available. So if the warps are basically waiting for a resource to become available, then it will wait for that.
So I guess both are theoretically useful based on that.
Yeah, both are important. So, but you can't control. I mean, if you want to change how you want to figure out whether the resource is available or not, then you have to change your code significantly. Because that is fundamental to like how the warp in itself figures out at runtime, determining whether a resource is available or not to dedicate whether a warp should execute or not.
Yeah.
Is that fair?
I think so. I think like there's also like just limits fundamentally to what the program counter sampling can get. Like in the end, like compared to what you can do with hardware waves, where you see everything at the same time, you're always going to be somewhat limited. And all of these things are kind of approximations of what the real bottleneck is.
Yeah. By the way, Eric, please ask this question when we have the Nsight team on this call, hopefully early next year.
Okay, yeah, great.
We were supposed to do it today, but did not happen. We were too slow in scheduling it.
Oh, I think I lost that one. That's a shame. I was going to show the thing in Nsight Compute where I've only got one of the 2L2 sites that's actually doing anything, but I don't think I've got the right thing open now. Oh well. Yeah, so basically in Nsight Compute, you will see this thing, which I'm kind of surprised NVIDIA even shows because it's basic. I cannot think of any use case for like an end user for this to be useful unless they're doing this kind of crazy thing I'm doing, which is the amount of traffic between the 2L2 sites, which is typically kind of identical to the traffic that to the L2 cache or to DRAM. Yeah, I think to the L2 cache. And those numbers basically just always match. But what I got in that kernel was this number basically goes to like 1% of the other ones, which shows that it's working. I'm not complaining that it's exposed. I'm just kind of saying, actually, there are things in here that are useless most of the time, unless you're doing crazy things.
Unless you're doing crazy things, that's important.
Yes.
Very, very, very important.
Yeah, I'm more used to kind of having to go like the row count, like the row thing, and kind of go to like a crazy column over here. So I'm not complaining. Just like there is so much information you can get in these tools that like very, very few users probably use, including myself. Most of the time, right, you don't actually need this. Like just looking at the compute workload, that memory workload, and then the stalls in source will tell you a lot of. It might not tell you exactly what's happening, but it will tell you what to focus on.
Arun, you basically said in the first slide of your presentation, we need two small nuclear reactors if we do the optimization, right? So we can save it. So there are people who try to do it.
Right. Yeah. I mean, I would hope so, because yeah, nuclear reactors don't feel like the first choice for most problems to me. Any other questions? You're welcome to just message me on Discord as well if you want to. If you've got anything else you want to ask afterwards.
Yeah, I might call it just to keep the sort of YouTube video underneath 2 hours. So yeah, thank you so much again, Arun. So for context textbooks, we don't have too many more talks for the rest of the year. We have one happening on Thanksgiving weekend, which is going to be about low bit ARM kernels. And then I'm going to be talking about Torch Titan and distributed computing as like our last lecture of the year. If there's people you think you would really like to hear from for next year, please let me know in general. Otherwise, thank you so much, everyone, and thank you again, Arun.
Thank you.